So let's continue with this some of these exercises. So today, last class we were just looking at this potentials called as Stillinger-Weber potential, and we saw another potential for the ionic crystals. So now I want to show you a simple example where Stillinger-Weber potential is used for silicon in order to say not do anything spectacular, but simply to print the variation of the energy with for various lattice parameters. So when you plot that, you should get a U-shaped curve, and the value of the lattice constant at which the energy is a minimum is basically the lattice constant that you get for that particular material for that potential. Okay, that's the goal. So before I do that, you all should be familiar with the folder where LAMMPS is actually installed. So I have installed it in some location in my computer. I have installed it right here, and if you look at it, you have the examples folder and then the potentials folder. So if you want to find out the interatomic potential for a specific material, then you might want to start off by looking at this folder right here. There are a large number of potential files, and if you open one of them, say for example, this is what we are going to use. Okay, if you open them, then in each of these files you will have, from which article this particular potential parameters was actually taken. So in this case it was Physical Review B volume 31 and 1985 paper was used in order to give you the various parameters for the Stillinger-Weber potential. Okay, so the Stillinger-Weber potential is a complicated potential with about 7 or 8 undetermined parameters which you have to give for the specific material in order for it to work. Okay, so what we are going to do is, I am just going to try to, there are several things that this exercise will do. The first thing is that it's going to, so far you have only been using the input file, and in the input file only you described all the interatomic potential parameters also, right? But now when it comes to a potential such as the Stillinger-Weber potential, you will have to specify the potential parameters in an external file and have LAMMPS actually read the parameters from that file. A couple of things you need to keep in mind when you are actually doing this sort of a thing, especially in the pair_coefficient command. The second thing is, suppose we wanted to do something for over a loop over several different values of, say, the lattice constant. You wanted to run the same file for several different lattice constant and then print out the energy, the lattice constant versus energy, and make a plot of it. So how do we do that? So this is going to be exercise 13, exercise 12. So I am calling my input file as swsi.in. Okay, so a lot of the stuff is pretty straightforward. So the units is metal units, atom style is atomic, and the periodic boundary conditions in all directions. Okay, and then what I want to do is, I want to create a lattice with some lattice constant A. Okay, and these are the basis atoms for this particular material. So it's basically a diamond structure. And then define a region, and then create a simulation box, create the atoms, and keep calculating, minimize the energy for that particular value of A, and then print out the corresponding lattice constant and the corresponding energy that I get, and do this for a large number of lattice constants. So I have defined a variable A which is of type index, which ranges from say 5.1 through 5.85. Okay. So all that we have to do is, in the lattice command you say custom, and you, instead of giving the actual value of the lattice parameter, you just give the variable name. So just give the variable name. So first iteration it will have the value 5.1, everything is the same, okay, and then I define the basis. There is only one particular type of atom here, so basis of all the 8 atoms is just 1. The mass of the atom is given here, and then here I define the pair style. The pair style is of type SW. So as you can see from the LAMMPS website, this is the LAMMPS website showing the expression for the energy for the 3-body Stillinger-Weber potential, okay, and you basically need to give the name of the file which contains that tabulated values of all the constants that you have to give for this particular potential. So, so you have these elements. So Stillinger-Weber files in the potentials directory are there. So this is just telling you that the potentials directory of LAMMPS has Stillinger-Weber potential, and you can identify it with the .sw suffix. But then in the actual file, what is there? So you have this is a 3-body potential, right? So you need to give 3 different elements. So depending upon what you are giving here, which order you are giving here, the parameters that are going to be chosen differently from this set of values. Okay, we are doing it for a homogeneous material, in the sense material with only one element type. So for this particular case, we don't really have to worry about it. But suppose you are doing it for silicon carbide, then you will have to be extremely careful. So that's actually clearly specified here in the manual. So for example, if you are doing just Si is the only thing, then the first element is basically in the 3-body term, the first element you give is basically the one that's right in the center. Element 2 and element 3, it's again silicon in our case, because we are just simulating pure silicon. Then the corresponding values of epsilon, sigma, A, lambda, gamma, etc., etc., etc. So some of these parameters such as A, B, P and Q are parameters which are going to be used only for the 2-body interaction. Say, if you look at it, there are so many different parameters that come in here, right? So for the 2-body interactions, you have A, B, P and Q are the only thing that's useful, parameters that are used for these 2-body interactions. Lambda, cos theta naught parameters are used only for the 3-body interactions, whereas the others like epsilon, sigma parameters are used for both 3-body and 2-body interactions. So the most important thing is this sentence right here. So while it is specified in a very concise manner, you really have to think about it when you are actually setting up your interatomic potential file. So for a single element simulation, you need to give only Si, right? It's not very complicated. However, if your simulation contains 2 elements, say for example silicon carbide, then every sentence in your interatomic potential file must contain an entry, and there must be 2 to the power 3 entries for each possibilities of the 3 different elements that you can have at the center and 2 at the sides. Okay, so you should have combinations for Si, SiC and so on. Okay, so I will show you an input file which contains for silicon carbide, just to illustrate how you do that. But for now, I just want to talk about the file which contains only silicon. Okay, so once you give these parameters right here, then the pair coefficients, so the pair style basically specifies what is the name of the interatomic potential that you are going to use. Whereas the pair coefficient, it tells several things. It tells you what type of atoms are actually interacting, what is the file from which you can obtain these potential parameters, and an elemental list which basically maps the element in the interatomic potential file to the atom type that you have chosen. So in our case, silicon is the only atom type. So there is only one atom type present in our system. So this Si is mapped. This Si is mapped to atom type 1 in our simulation. Okay. Suppose we did this. Okay. Then what am I doing? I minimize the structure for this particular value of A, and then I define a new variable lat con equals $A. Basically, lattice constant is equal to the value of the A, and then in thermostyle I print the variable lat con and the corresponding potential energy, so that my thermodynamic file will actually have that information. But when I use a thermostyle, I need to do a run. If I didn't do a run, nothing gets printed. Okay, so I just say run 1. That means in it's just going to do one step, and it is going to print out the corresponding lattice constant and the potential energy that it calculated at the end of the minimization process. Then I say next A. That means of all the A's that it is present here, it takes the next value of A, and then I say clear, and then I say jump swsi.in, which means rerun the contents of this file. swsi.in is actually the name of this script. Okay, so it will rerun the contents of this script, but before doing that, you need to make sure that you have performed a clear. Okay, if you don't do clear, it will complain. So let us see what it does. So let me just run it. What happens? So it's done. So it's given you, it's ran it for all those values of A here, and if you open your log.lamps file, it's printing these potential energy for each of those lattice parameters, which is of course changing, right? And in all the cases, I think the minimization has just exited with energy tolerance. The energy tolerance is reached. Okay, so it's done a good job. So now from this you can basically extract out only those lines which have the potential energy using various grep commands or any Unix command. So what you can do is grep say minus A1 put energy log.lamps. So it gives you all the line that's just after the sentence which has the string potential energy. Okay, but then I don't want this I don't want that line either, so I again do a grep minus v put eng, so that contains only the lattice constant and the energies, right? And then you can get rid of those dashes and basically make a plot of the energy for every lattice parameter, and you see that the lattice parameter is the minimum value of the energy is obtained for some lattice parameter between 4 and 5.4 and 5.45. So if you check the literature, you will find out that the lattice constant for which this potential was fitted is actually this value. Okay. So see, this example actually took very few, didn't take too long to run. So all your simulations, before starting on anything large, you should do such simple exercises to make sure that the values that is predicted by the interatomic potential for which it is fitted for is somewhat reproduced by your simulations. Only then we are using the interatomic potential correctly. Now let us take a look what happens if you did not. So there are a couple of things that I did there, right? So I said clear, I said next A. So obviously next A is kind of clear, it just means use the next value of A. If I didn't do the clear, units command after simulation box is defined. So the previous run, it had defined a simulation box. When it is running again, if I did not clear the settings, it redefines the units command, which is wrong, right? So when you do clear, there are a couple of things that basically is deleted from the system's memory, and you are able to run a second simulation. So basically what it does is something very specific. See, this command deletes all atoms, restores all settings to their default values, and frees all memory allocated by LAMMPS. Once a clear command has been executed, it's almost as if LAMMPS were starting over again with only the exceptions noted below. So there are exceptions, which means the variable and all is not deleted. It still remembers what the next A is. Okay, this command enables multiple jobs to be run sequentially from one input script. These settings are not affected by the clear command, the working directory shell command, log file status, echo status, and input script variables, which is basically the variable command. Okay. So this is extremely useful, right? Once you know how to do stuff in a loop, you can run your simulations for various temperatures, for various pressures, right? So that's one thing that I wanted to demonstrate here. So this is the example with this Stirling-Weber potential, and the pair coefficients in this particular case just had a wild character, basically saying that you have to span all possible atom types, for which I am giving you the interatomic potential file here. But it is possible that your interatomic potential might require interaction between atoms of different types. For example, if you are going to simulate the interactions of ideal gas containing argon and krypton, so okay, they are atom type 1 and atom type 2, then you would have to have interactions between argon-argon, krypton-krypton, and argon-krypton, right? And they have different values, right? They will have different values. So for each and every possible pairs, you will have to specify the corresponding pair coefficient, the atom types there. So here each star means all atom types, between all atom types, but star n means all atom types from 1 through n, including n and 1. Okay. N star means all atom types from small n to capital N, where n is the total, capital N is total number of atom types. So n star n means all atom types from m to n. Sorry, this should be m to n. So you can give here something like this. So if there are 4 atom types, interactions between atoms of type 1 to 2 with interactions of atoms of type 3 to 4 are going to have some set of coefficients here. It's not applicable for this example, but imagine your Lennard-Jones case where you actually specify epsilon and sigma and the corresponding cutoff. Right. So instead of choosing each and every one, suppose you had 20 different atom types, then you could in principle do something 1 to 10, 11 to 20 to describe the interactions between one through 10, all atom types of 1 through 10, with all atom types of spanning from 11 through 20. Okay. Of course, you will have to give other interactions as well. This is just one set, right?
10 power 10. 10 power 10.
No, 10 power 10 interactions. Possible. This is just an example. So let's give one. Seems huge, right? So 1 to 2. 3 to 4. Yes. No, that's what, to give those many, the idea is to give so many interactions, you don't have to like type each and every pair is what this command helps you do. If they are having the same set of sigma epsilon values.
Oh, so this is only for one one particular sigma.
Yeah, exactly.
If they are changing any
You have to give additional lines with the corresponding pair coefficients. You have to add other pair coefficients to take care of other interactions.
will it read from a file that will it match on its own?
It will not match on its own. You have to give what element you are matching to. So, for example, in this case, the SI that you are giving here, is actually the same label that appears in the potential file here. This label that's appearing here. So that could be A and this could be AAA. Because it appears first, that element Si or A is going to be mapped to atom type 1. Okay. So what this means is, one more way of explaining this is to actually say, for example, just for the heck of it, 8. So there are 8 atom types. I just said there are 8 atom types. Did you see that? I just said there are 8 atom types. Basis atom 1 is of type 1, basis atom 2 is of type 2, basis atom 3 is of type 3. I just said that, and then I just said in my pair coefficient, this is si.sw is the name of the file, and each of these labels Si should map to the corresponding type that is generated, right? So each of these is so you can imagine if it's more than one. So if it's silicon carbide, then you would, if in your input file you modeled Si to be of type 1 and C to be of type 2, then you would do this. But you can also do this provided you keep track of which basis is carbon and which basis is basically silicon. Now this is easier said than done. It can get really confusing when you are actually doing it for these multi-body potential. Okay, so I will try to give you an example where we do a Tursoff potential where exactly the same type of input file actually has to be given. Yeah.
If I use 1 star 2 and 3 star 4, does it mean that
What is that? If I use
pair coefficient, I use 1 star 2 and 3 star 4.
1 star 2 and
3 star 4.
huh.
Does it mean it includes only the interaction between 1 and 2 and 3 and 4?
No. 1, 2 and 3, 4. All atoms of types 1 through 2 including 1 and 2 with all atoms of type 3 to 4 including 3 and 4.
So it includes 1, 3, 1, 4,
2, 3, 2, 4. Yes.
but it does not include 1 with 2.
Yes. You will have to give that. Yes.
So for this particular when we write this pair coef,
Uh-huh.
we should know what the structure of that file is, because you have to
Yes.
use the same
Label. Yes. You are generating that label. You are generating that file.
But in this case,
We took it from, otherwise you will have to generate. You could call it ABC and put ABC here. It should work fine. Now another important form of the intraatomic potential is basically the embedded atom method. Okay, so the problem is, see, in all of these examples that I am giving you, I am just going to do how to specify the intraatomic potential file and do a simple plot the lattice constant versus energy, because minimization and doing other exercises on that is kind of similar to what we have done for argon, right? At least the kind of fixes that you must use, all those things remain pretty much the same. Okay. So why do you need, there are other kinds of, right now whatever we talked about were called potentials, right, pair potentials, which basically pair potentials or three body potentials, which basically was a reflection of the fact that we could truncate our intradynamic potential at some point. So this is the 2 body, this is the 3 body, and then you have the 4 body and so on. We just said that anything after this is actually not important and we stopped with it. So we did Lennard Jones is 2 body and then Schilling-Weber is 3 body potential. But it so happens that for in some cases like metals, the higher body potentials do not converge quickly to a value. So you really cannot neglect all the higher order potentials, so to speak. But it is also inconvenient to use all the higher order potentials for obvious reasons. You have more combinations of R, alpha, beta to actually take into account, and it is very difficult to come up with functional forms that will actually do this. So people have come up with something referred to as functionals. Okay, the name functional is used wherever the interatomic potential form does not appear like what it does here. It's called a cluster potential. It does not appear like this. The functional form does not appear like this. Then it is called as a functional. Okay, the interatomic potential form of the function does not look like that, so it's called as a functional. And there are interatomic potential models which are actually not looking like that, and they are classified into 2 categories. One is pair functionals and other is cluster functionals. So pair functionals, as you can imagine, require only they still require only distance information, but the functional form will not look like that. Okay, and cluster functional involves group of 3 or more atoms. Okay, so an example of the embedded atom potential is like this, which is very commonly used for metals. Okay, embedded atoms. So it's kind of capturing the fact that your atom is actually embedded in a sea of electrons. So basically the energy depends upon the energy of the electron gas that is basically surrounding that atom. So that is the basic idea. Of course, there's a lot of physics as to why that form of interatomic potential is appropriate for such systems. We are not going to deal with that. We just want to know what this embedded atom does and approximately and somewhat understand, how to use it when you are trying to do simulations with LAMMPS. So embedded atom method, this is the functional form. It consists of a pair function plus the embedding energy term, okay, which depends on rho alpha, which is again the local density of the electron gas. So V alpha is viewed as a Coulomb interaction between atom. It is not actually Z alpha, Z beta and all that, it's something else. And U alpha is the electronic energy associated with the embedding of the atom alpha in a sea of electron or electron gas of density rho alpha. So, so that's what this is. And in LAMMPS, the interatomic potential for these systems are actually given in the form of a table. It's a huge table. Okay, there are different formats in which embedded atom method potential files can be given, and this is one of the formats that LAMMPS can understand and use. Okay, so I will open the file. So for the style EAM, a potential file must be assigned to each II pair of atom types by using one or more pair coefficient commands with a single argument, which is basically the file name. So when you look at the input file, I have done exactly the same thing that I did with silicon here, where I just want to find out the energy versus lattice constant curve. So I have a variable index and so on and so forth. Let's not, the only difference is that I just construct an FCC lattice, and the only thing that I have to give here is $A, basically the lattice parameter. And another thing that I want you to notice is that here I have given the region in the default units, which is lattice units, not units box, the lattice units, because if it is units box, then I have to every time calculate what my box size is. When I say lattice units, it's just going to be automatically taking 10 times the unit cells in each of the directions. Okay, so I give star star and then call the corresponding file which is there in the same folder called al_jnp.eam. Perform minimization and everything like what I did for the silicon file, and if you run it, you're going to get the energy variation. But it's a good idea to look at the okay, let's look at the so you get something that looks like this when you plot the energy versus lattice constant. The first thing that you notice is that the lattice constant is somewhat a little bit less than 4. Okay. If you open up the potential file, the first line in the potential file is basically a comment and it's not used anywhere. The second line basically gives the atomic number, atomic mass, the lattice constant that was obtained from this potential, and the crystal structure that is used. And then you have another line which tells you how the function, it's a tabulated value of the function f of rho for various values of rho, and the function and another function z of r for various values of r. It's basically the part of the two body potential phi. Okay. So if you take a look at this, it says that there are 500 entries for f of rho. So there should be 500 entries starting from here. So going like this. So if you count 1, 2, 3, 4, 5 and so on until somewhere here. So there will be exactly 500 entries, and then another 500 entries for the value of the function, and then the corresponding values of, let me take a look at the file. The density function rho of r. Okay, the density function rho of r, how rho varies with r, the effective charge function, how that varies with r, and the embedding function f of rho, how that varies with rho. Okay, and how rho and r are split is there in this information. D rho and dr contains that information, which is d rho, how the density is split and how the distance is actually split. Okay, so that is the embedded atom potential, and most of the time you will be able to obtain these embedded atom potentials for whichever ones it exists. Okay, usually it can be a hard time to find for arbitrary alloys, and you should what is the name of that? NIST, interatomic potential repository, basically contains all possible interatomic potentials that might be there. Okay, unless new ones are invented and they have not yet been updated, you will find most of the information in this website. So you can take a look at this and get all the information of the potentials for which you have the interatomic elements for which the interatomic potentials basically exist.
Number.
Yeah.
In the previous cases, we did not mention atomic number. In this case, why is it necessary?
It's probably used by the interatomic potential somewhere. I don't really know how the interatomic potential has actually been developed. Okay, so it is possible that it is going to get used somewhere in the interatomic potential functional form, which is inside LAMMPS.
And in case of Leonard Jones, we were writing pair style LJ/cut and the cutoff length.
Correct. Ij epsilon sigma and then the corresponding cutoff radius. Yeah.
So in case of EM, we don't need any cutoff distance or anything.
It's there actually. It's right. You don't have to explicitly specify it. It is there in the file. This is the cutoff.
Okay, so we don't have to specify it in pair style.
Yeah, you don't have to specify it in pair style for the EAM potential. So now you can imagine we plotted the variation of energy with lattice constant, right? So this amounts to plotting the variation of energy with volume as well, right? Because A cube is nothing but the volume. So which means you should be able to find out approximately the bulk modulus of the material. If you just plotted this energy for various volumes, then dou E by dou V, 1 by V times dou E by dou V should actually give you the bulk modulus of the material at low temperatures. And for material at low temperatures, right? For because and for metals and ceramics, for really low temperatures like close to 300 or 400 Kelvin, unless you are like close to its melting point, for temperatures far away from the melting point, the bulk modulus and the Young's modulus, the mechanical properties of the system are not significantly affected by temperature. So you can get a rough estimate of these mechanical properties also by making a plot of this energy versus the volume. So I think that you should be able to do.